introduction. First of all, I would like to thank organizers for the opportunity to participate in this event. This work was done in collaboration with Mikhail from Harvard University and with Andreev, who is somewhere here today. The outline of my talk is the following. First of all, I will talk a bit about the Josepson effect. Of course, everybody knows here about it, but I would like to clarify some points which are important for me. And then I will talk about the non-equilibrium effect, and in particular the non-equilibrium effect in Andreev interferometers under the thermal bias. Well, if you put two superconductors together, then there is a non-dissipative current flowing across the interface. And it's important to control somehow the properties, the magnitude of the current. It can be done in many different ways. We can control phase difference, we can change temperature, we can, of course, choose geometrical parameters, we can apply magnetic field or electromagnetic radiations, and many others. For instance, we can choose geometry. We can make a constriction here. Sorry. What happened? For instance, we can make a constriction here or place different materials in between two superconductors. I will talk about the SNS structure when there is a piece of normal metal is placed between two superconductors. Then we know that due to proximity effect, superconducting correlations penetrate into the normal metal. And they decay exponentially if we go deep into the normal metal. And the length of the decay depends strongly on energy. If we, in the diffusive limit, the dependence is the following. And from this, we immediately obtain important parameter of the structure, the Taurus energy. You see that if the energy is less than Taurus energy, then the decay length of the superconducting correlation is just the size of the system. So we can say that there is a coherence between two superconductors. But if we consider quasiparticles with high energy, we immediately obtain that such quasiparticles couldn't maintain coherence in this system. That's important for my talk. And from this simple consideration, we can immediately obtain the temperature dependence of the Josepson effect in equilibrium. It just is such integral, whereas this term, red term, is just a measure of the overlap of these two functions, and this hyperbolic tangent originates from the Fermi distribution function. Then we can take this integral, transforming it into the sum of the Matsubara frequencies, and in this temperature interval, when the temperature is less than energy gap but higher than Taurus energy, we get fairly simple result that the amplitude of the Josepson current is exponentially suppressed with increasing temperature, and the phase dependence is just the sign. Here I just summarize important energetic parameters of the structure. It's the temperature. The next parameter is the gap. In the following, I will assume that the gap is the largest parameter of the structure. So I assume that the temperature and Taurus energy is much less than superconducting gap. And in the following, simple expression will be obtained in the limit when the temperature is in between the tau loss energy and energy gap. And for simplicity also I assume that metallic region is short enough so that we can disregard the inelastic process. That is just the system under the consideration, the Andreev interferometer. There are two superconducting terminals, two normal terminals, which are somehow interconnected with quasi-one-dimensional normal wires. We can incorporate this system into the external circuit in many different ways. For instance, we can connect two normal terminals via battery. Then we get a restriction on the voltages. Just the difference of the voltages is just V, the battery voltage. And we have a restriction on the currents. The currents flowing into the one normal terminals, the sum of the currents flowing into the normal terminals equals to 0. Or we can consider another situation when the normal terminals are not connected to the external circuit at all. Then we have a condition that there is no currents flowing into the normal terminals, but some voltages can be induced there in order to provide these conditions, the absence of the current. Here is just, I show one of the example, well-known example. Here's actually the same structure I showed you before, two superconducting terminals and two normal terminals, and the voltage applied to the normal terminals. And we're asking what is the Josepson effect in such structure. As we apply the voltage, then we should modify the equilibrium distribution function and replace it by this one. And of course, we expect that as soon as quasi-particle distribution function is not equilibrium, then the Josepson effect should be different from the equilibrium one. And it does indeed the case. We have an expression for the equilibrium distribution function, just an integral of the product of the spectral current and Fermi distribution function. We should simply replace the distribution function by the non-equilibrium one. And what is important that the spectral current is the oscillating function of energy, and changing the voltage, we can choose which energies give the main contribution to this integral. And indeed, it was done by these guys. Indeed, changing the voltage, we can control the value of the Josepson effect in this structure, and even get the zero pi transition in this structure. Also, I would like to mention the thermoelectric effect in the Andreev interferometers. If we maintain normal terminals under the different temperatures, we can expect that some voltages induced here. And we can introduce the Seebeck coefficient, just the ratio of the voltage difference divided by temperature distance. And the main surprise here that the thermoelectric effect in such structures with superconducting terminals is much larger than the corresponding normal structure. That is because of the interplay of the conventional scattering and Andreev reflection. I won't go in details here, but I would like to say that even such simple structures such as Andreev interferometer actually have plenty of non-trivial phenomena. And let's now switch to the main part of my talk. I would like to consider much simpler Andreev interferometer with the length of the normal wires connected to the superconducting terminals of the same layer. I maintain normal terminals under the different temperatures, and I would like to calculate the Josepson current flowing between the superconducting terminals. In this geometry, actually, voltages are not induced. This is because of the symmetry of the system. And this simplifies consideration a lot. I used the approach of the Uzadel equation here, which I believe relevant theory for dirty systems. The central object here is the quasi-classical green function. If we somehow solve Uzadel equation and find this green function, then we can calculate the current density everywhere in the system. Green function has three components: retarded and advanced component of the green function describe the spectral properties of the system. And the Keldysh part of the green function contains information about the quasi-particle distribution functions in the system. And it's convenient to parameterize the Keldysh green function by two distribution functions. If we substitute this ansatz into the Uzadel equation, then we get two diffusive-like equations for the distribution functions. Here, dt, dl, and y are some kinetic coefficients. They strongly depend on energy and phase difference in the superconducting state due to proximity effect. In the normal wires, they depend on the energy and phase. And G is spectral current. In the normal state, without the superconductivity, dt in dl simply equals to unity, and coefficient y and spectral current equals to 0. And this equation, the diffusion-like equation, should be supplemented by boundary conditions. That is the distribution function, quasi-particle distribution function in the normal electrodes. That is, it's this. And of course, due to diffusion into the, across the system, the distribution function inside the structure strongly deviates from this simple expression. And okay, in the partially symmetric X junction, there's a large simplification, because I said that there is no induced voltages there, so that the HT distribution function equals to 0 identically. And also, again, due to the symmetry, there is no y kinetic coefficient. Y kinetic coefficient equals to 0 in the wires connected to the normal terminals. As a result, these equations reduce to the fairly simple one. In the wires connected to the superconductor, we get just the equation that the distribution function is spatially constant there. And in the wires connected to the normal terminals, we get this diffusion equation. Of course, it can be easily solved in the quasi-one-dimensional geometry, and the result is the following. The result, it's convenient to introduce two parameters in this system. I called them spectral resistance. If we this spectral resistance in general depends on energy and phase difference, but if at large energies dl tends to unity, and this spectral resistance is simply the normal state resistance of the corresponding wire. So we can say that this spectral resistance is just the resistance of the wire at a particular energy. The energy dependence, again, arises due to the proximity effect. And then we can just write, solve the equation and write the distribution function inside the system in this form. You see that it is a weighted sum of the equilibrium distribution functions with some weights which depends on energy and phase difference. It's convenient to rewrite this expression in the form where the weights are not energy and phase dependent. It can be done, but the additional term appears here. It's function W. Actually, we can't evaluate the function W, but it's again some combination of the spectral resistances. What we know about this function, that it is even in the energy and phase and rapidly decays when the energy exceeds the Taurus energy. So now we have all ingredients to evaluate the current. Sorry. We just have this expression for the current. We should substitute here the non-equilibrium distribution function. As a result, we get three terms. Integrating this term, we get just the equilibrium Josepson current evaluated at the temperature T1. Integrating this term, we get again equilibrium Josepson current evaluated at the temperature T2. I call these two terms as just quasi-equilibrium contribution to the Josepson current. And the last term is just the integral over this term. It's the essentially non-equilibrium contribution. And what is important, I will show you that the temperature dependence of these terms are very different. You see that integral representation of this term looks like similar, while the temperature dependence should be very different. But actually, there are one important difference between these two expressions. The point is that the spectral current G is actually a real part of the analytic function in the upper half plane. But from the other hand, the function W have no any particular analytical structure anywhere. And that is the essential point. Evaluating this integral, we can use Matsubara technique. And in the temperature interval, when the temperature is much larger than Taurus energy, we immediately get well-known result that the equilibrium Josepson current exponential decay with the temperature. From the other hand, we can't use a Matsubara trick here in the non-equilibrium term. In the leading order, we can simply expand the hyperbolic tangent in Taylor series, and in the leading order, we get this very simple result. So without actually any particular calculations, we get the temperature dependence of the non-equilibrium contribution. And we see that instead of the exponential dependence, we get just one of the T dependence in the non-equilibrium contribution. It's actually the main point of my talk. You see that non-equilibrium contribution in the thermally biased junction can be much, much larger than the equilibrium one because of the different temperature dependence. That is indeed the case. Using some dirty tricks, we can actually evaluate the function W and find the phase dependence of the non-equilibrium contribution and the prefactor here. And you see what is important, that non-equilibrium contribution first depends on temperature only as 1 over T, has quite unusual phase dependence. And the third, the sign of the non-equilibrium contribution depends on the geometrical parameters. So changing the geometrical parameters of the structure, you can change the sign of the non-equilibrium contribution to the Josepson current, or just changing the temperature. You can also change the sign. And that is important. Here's the shown the result of the numerical calculations using just Uzadel equation without any approximation and our formulas. You see that at low temperatures, quasi-equilibrium contribution to the Josepson current dominates, but that is the temperature dependence of the critical Josepson. That is the critical Josepson current as a function of T2 when the temperature T1 is fixed. So at low temperatures, the quasi-equilibrium contribution to the Josepson current dominates, but starting with some temperature, non-equilibrium contribution becomes strong, and actually the critical current increases starting with some temperature. Here I plot the dependence when the length to the first terminal is larger than the length of the wire to the second terminal. In the opposite situation, we get a similar picture, but now the sign of the non-equilibrium term is opposite. So at low temperatures, when the T2 is low, we get this black curve for the current phase relation, and we see that just conventional, slightly modified sign dependence. But when the temperature becomes higher, then we see that the junction switched to the, I said, almost pi state. So in the thermally biased junction, changing the temperature, we can switch it from the 0 to pi state. Actually, we can generalize these results to the Andreev interferometer or the general geometry. And again, we can show that the total current flowing from one superconductor to another can be represented as a sum of the three terms. The first two terms is just a weighted sum of the equilibrium Josepson current evaluated at the temperatures T1 and T2. And the third term is essentially non-equilibrium contribution. And again, we can show that the non-equilibrium contribution has this particular one of the T dependence, which again can dominate the equilibrium contribution at large enough temperatures. And for X junction of the general geometry, so there is no restriction of the length of wires, we can obtain this approximate result, which shows that the sign of the non-equilibrium contribution again can be controlled by the temperature or the junction geometry, and has this particular phase dependence. And what's important that this function P1, it's just a universal function, doesn't matter, but it can be large. What I can say that tuning the geometrical parameters, you can enhance even larger the non-equilibrium contribution, so that it can be observed at lower temperatures. So this effect of the thermal bias can be larger. that is the summary. We proposed a new type of the junction, thermally biased Andreev interferometer, which can be parameters, so the junction can be tuned by the temperature. And we find it's quite unusual that changing the temperature, we can switch with junction from 0 state to the pi state. And what's important, the temperature dependence of the Josepson current is 1 over the T, the dependence of the non-equilibrium correction. So one can think about the situation that in the equilibrium there is no Josepson effect. It negligibly small, but applying the thermal bias, we can obtain Josepson effect in this system. Thank you for your attention.
Thank you. So the talk is open for questions.
Could you tell us a little bit about the material, so to say, absolute numbers involved? Bias, how many Kelvin and current of how many amperes? This, for instance, you have all in this ETH measure, which is what I mean.
This is just conventional Josepson junction, so it depends on how to prepare it. Here's, you show that in this partially symmetric junction, non-equilibrium effect can be observed if the temperature is about the 50 of Taulis energy. So you should quite long.
Okay, but that is precisely my question. When I look at this figure, 50, how many Kelvin should I imagine is this 50? Also this 10 to the minus 4, how many amperes should I imagine in a real device this would be? If you actually made such a device, you would be dealing with kelvins and amperes. And I'm just asking to translate this graph into an actual laboratory measurement. What numbers I should expect on the two axes in Kelvin and ampere?
Oh, of course, if you have a critical temperature of the superconductor about, say, 1 Kelvin, then of course you here at sub-Kelvin temperatures.
And if I have, say, 39 Kelvin, like magnesium diboride, then what is 50 here?
Well, I will say that for simplicity here, we consider the situation where the temperature is much less than the superconducting gap and much larger than the Taulis energy. But actually, the first restriction that the temperature is much less the superconducting gap is not too restrictive. So this temperature can be around the superconducting gap, so of order of.
Okay, thank you.
Just the condition that the temperature is quite low allow us to disregard the overgap contribution to the current. If your temperature is large enough, then we should take into account that. But I believe that the non-equilibrium contribution to the current, which is 1 over the T, still be there.
So, is it possible to calculate the thermophase Seebeck coefficient in this geometry? People have calculated it in the thermophase Seebeck coefficient. Can you calculate? Means or this geometry? Because people have calculated it for simple Josepson junction. If there is a thermal bias between, so you
This
can.
one, I don't understand, sorry.
The question is that is it possible to calculate a thermophase Seebeck coefficient for this geometry? Means in Josepson junction, if there is a thermal biasing between these two reservoirs, then there is this called thermophase Seebeck coefficient.
It's the thermoelectric coefficient.
Yeah.
Yes, of course it's possible, but it's the topic of the, say, in our talk. I just, of course, we have several works on the topic of the thermoelectric coefficient in the Andreev interferometers. There is actually a lot of interesting effects there, but it's just not the topic of today's talk.
Okay.
Okay. Any other questions?